This video will talk about how to deliver maximum power to a load. Typically, you will have a circuit of some variable number of sources and resistors, and we'll have two ports coming out, A and B. And the question would be, what is the value of RL that is able to allow maximum transfer of power from this device to it? So the first thing you have to do, the step one for this process, is we need to make sure come up with the Norton equivalent of that device. Of course, is going to be R Thevenin, and there are many videos earlier that help help guide you through the process of finding a Thevenin equivalent. But once you have the Thevenin equivalent of the device, then now we can start looking at the analysis of what kind of load will allow maximum transfer of power between those devices. This is a pretty important conversation because if a company is generating a bunch of power, they want to be able to deliver that maximum benefit to the customer, and they don't want to be losing that power. So we are looking at how to do that. So the first thing we have to do, we have to determine what is the power that is delivered. We know power equation is I squared RL. That would be the power that is delivered to the load. And of course, doing a little KVL, we can determine I is V Thevenin divided by R Thevenin plus R load. So this equation basically becomes V Thevenin squared divided by R load plus R Thevenin squared, and all that multiplied by R load. Okay, so here we are now in calculus. I'm sure you have studied that if I have a power is variable with an equation. In this case, RL is the only variable we have. So in order to find out what the maximum or the minimum is, maximum, we want to find out the time when, or in this case, I'm sorry, not time, because time is not the variable here. The variable here is the question here is at what value of RL we're going to get P max. And we know that is going to happen when the derivative of P with respect to RL is equal to 0. So once we do that, we can, and I'm not going to go through the derivative process here. So you take a derivative of this entity, and the only variable, of course, is RL. So you can go ahead and do that. And the bottom line will be that in order for this to occur, for this derivative to be 0, one thing has to be true. RL has to be equal to R Thevenin. So that's the rule. That will make sure that the load receives maximum power. So if you want your load to receive maximum power, you got to make sure those are equal. Now, if somebody asks you what is the maximum power, all you do, you replace everywhere you see R Thevenin with R load or vice versa, and then this equation gets simplified to basically V Thevenin squared divided by 4RL, and since R and R Thevenin are the same, you can also write that as 4R Thevenin. So here's basically what we do. Now let's kind of take a quick example here. Let's say someone gives you this circuit and says basically at what point would this get the maximum power. So the only thing you have to do, you will take the RL out of here, and then you will find the Thevenin equivalent with respect to A and B. Of course, this doesn't have any independent sources in it, so you can just do an R Thevenin is equal to R AB equivalent when all the sources are deactivated, and follow that process to find R Thevenin. We've done that here, and that's the answer we got. Therefore, the only value of RL that would deliver the maximum power is got to be equal to R Thevenin, and it's equal to 10 ohm. So here is, so the two rules you have to remember is if someone gives you a device and asks you to deliver maximum power to RL, you remove the RL first, find the Thevenin equivalent of the system, and then once you found that, then the only thing you have to make sure is that RL is equal to R Thevenin. And if somebody asks for a maximum power, you can give them the equations which are provided here. You can use this equation to give them the maximum.